Okay, here we go. We're going to start out the first video of section 9.6 with a word problem. This whole section here is about applying our sine and cosine functions to real life situations. That's a question that I get a lot is how does this apply to real life, or when am I ever going to use this? So the reality is that there's sine and cosine waves all around you all the time. Sound is produced using waves, and those follow sine and cosine patterns. So let's look at this first problem. A sound consisting of a single frequency is called a pure tone. An audiometer produces pure tones to test a person's auditory functions. An audiometer produces a pure tone with a frequency of 2000 hertz. That's cycles per second. The maximum pressure P produced from the pure tone is 2 millipascals. Write and graph a sine model that gives the pressure P as a function of the time in seconds. All right, now I know what happens for a lot of times. People read a word problem and immediately psych themselves out because you think it's too complicated or you don't understand. Don't let some of this vocabulary throw you off right here. There's some stuff in here that we can just pull from, and we don't really need some of the other information. So all this is saying is that we have a pure sound wave, a pure tone. So it's a consistent wave. So that means we can model it with a sine or cosine wave. Now let's look at some information about our wave. It says that our pure tone has a frequency of 2000 hertz, which is cycles per second. Now the relationship between period and frequency, the frequency is the number of times something happens. So we have a frequency of 2000 cycles per second. That means there's 2000 waves per second. So there's a lot of waves happening in a short amount of time. The relationship between period and frequency is as follows. We've got, sorry about that. All right, so we've got the period is equal to 1 over the frequency. Let me make this a little bigger. Period is equal to 1 over the frequency. What that means is if we know that something's happening 2000 times in 1 second, the time it takes, or the distance it takes for one of those to happen is just 1 over the number of times per second. So if we have 2000 cycles per second, our period is going to be equal to 1 over f. Another way we can write that is the opposite. The frequency is equal to 1 over the period. Okay, so that's our relationship between period and frequency. The maximum pressure is 2 millipascals. That's going to relate to our amplitude. So let's go ahead and click through this. So what we need to do, we first need to find the values of A and B for our model. Okay, so this is what our model is going to look like. We're writing pressure as a function of time. So P is going to equal to A times the sine of B times T. So B is our period and A is our amplitude. Now, since we know the maximum pressure is 2, that's our amplitude. Okay, our amplitude is just going to be the pressure. So now we need to use the frequency to find B. So we're going to use that relationship I just talked about. So the frequency is equal to 1 over the period. Okay, so we can use this to find our actual B value. Now, if you remember, the period is just equal to 2 pi over B. So if we have, in this case, sorry, wrong button keeps hitting. If we have 2 pi over B equals our period, then 1 over our period is just B over 2 pi. Okay, 1 over the period is just going to be the inverse, which is B over 2 pi. That's how we get that equation right there. So here we've got our first one, 2000 equals B over 2 pi. Now it's just simply solving for B in this case. So we multiply both sides by 2 pi, and we get our B value is equal to 4000 pi. So what we're doing is we're using this information here to figure out what our transformations are. So we have an amplitude of 2 and a b value of 4,000 pi. So what that means is our equation is going to be p equals 2 times the sine of 4,000 pi t. Okay, 4,000 pi is our b value, t is our variable, and 2 is our amplitude. So that's the first part of this question. We have to write an equation. Now, when it comes to graphing, let's just do a quick review of graphing the sine function. Remember, in our parent function right here, if we have sine of x, in sine of x, our period goes from 0 to 2 pi. So 2 pi is the period length for a standard, our parent function. Pi is the halfway point. And remember, the points that we find are the midpoint, the maximum, the midpoint, the minimum, and the end point, which is a midpoint. Now, in our sine curve, sine wave, our amplitude is 1. So our sine wave looks like this. We come up, and that's what 1 period looks like of our sine wave. Okay, we go from 0 to 2 pi. Now, to graph this, we need to go ahead and apply these changes to it. So first thing you want to notice, since we've got a b value of 4,000 pi, this period length is going to be shrunk, extremely shrunk. It's going to be much smaller than 2 pi. That's because we have 2,000 cycles happening in 1 second. So let's go ahead and apply those changes. So since we know that the amplitude is 2 and the period, which is just 1 over f, our period is 1 over 2,000. So that means our one complete wave is going to happen in the distance from 0 to 1 over 2,000. The 5 key points, remember, we find our midpoints, which are the intercepts. That's at the start. That's at the end. So 0 and 1 over 2,000 is our end point. Our midpoint, again, I'll put this sine curve back up here for you. If we look at our sine curve right here, remember, we've got our 3 midpoints are at the end of our period, the middle of our period, which is halfway through, and then at the beginning of our period. That's how we get these 3 values. The starting point is at 0, 0. The ending point is at the end of our period and the midline. And the midway point, we just take 1/2 and multiply it by our period. So we get 1 over 4,000. Okay, so those are our 3 midpoints. The other key points that we have to find are the maximum and the minimum. Now remember, from class and from last section, the maximum point is at 1/4 times your period, and the minimum point is at 3/4 times your period. And in this case, because our amplitude is 2, these are going to be at +2 and -2. So let's go ahead and get the key points here. The maximums are, like I said, just going to be 1/4 times the period, which is going to be 1 over 8,000, and then our maximum is 2. The minimum is going to be 3/4 times 2,000 and -2. So 3 over 8,000 and -2. So you'll notice nothing's different. We're doing the same process. We're finding the key points, and we use the amplitude and period to find those. So when we actually graph this, here's what it's going to look like. Now notice, sine curve looks exactly the same, except the only difference is, look at our interval right here. We have our maximum is at 1 over 8,000. Our midpoint is at 1 over 4,000. Our minimum is at 3 over 8,000. And our maximum, or our final midpoint, is at 1 over 2,000. So this is a very short period of time, a short interval right here. If we were to extend this out or look at this on Desmos, you would see that this is a very tight, compact graph. In fact, we can actually do that. Let's look at 2 sine of 4,000 pi x. So if we go to Desmos, And let's graph 2 sine of 4,000 pi x. And look what we get. This is so compact here. Look how far we have to zoom in to actually get anything. We're zooming in to just fractions. You see, if we go ahead and change the date here, let's go on the x-axis, or change the intervals. Let's go from 0 to, how about our step is 1 over 2,000. And then for our y-axis, we'll go from -1 to +1. Okay? And we'll keep this in radians. And let's do this again. We've got 2 sine of 4,000 pi x. Look what we have now. Here we can actually see our sine function graphed. And look what we're doing. One interval here goes from 0, 0 to 0.0005. That's 1 over 2,000. Okay, so you can see this looks just like our sine curve that we've been working with. However, our period is just extremely small. That's why we have to zoom in so much. That's why if you zoom out on this, again, you see that there's so many cycles happening that it just starts to blend together into just one compact, just one thick line. So that's why it's really important to understand the period of these. So this is common for sine waves or any waves in real life because there's so many of them happening. 2,000, a frequency of 2,000 is very common. So, you know, when you talk, there are thousands of waves going up and down per second from your sound wave. All right, so now that you've seen this, you're going to have another problem that's just like this, so make sure you come back. If you have any questions, you can rewatch it through, you can pause it, take more notes. Use Desmos. I encourage you to use Desmos and play around with some of these different functions. The problem that I want you to do is this right here. An audiometer produces a pure tone with a frequency of 1,000 hertz. The maximum pressure P produced is 20 millipascals. Write and graph a sine model that gives the pressure as a function of time. What I want you to do, the things that I want you to answer in your question, I want you to give me the sine function, so write out the actual function for this. I want you to write the amplitude and the period and your 5 key points. So you're writing down the sine, amplitude, period, and your 5 key points for this function. Again, go back and look at the example to see how we get those points. I don't want to see anyone saying I don't know or leaving anything blank or just writing in random numbers for your answer. Make sure if you have a question, you email me or send me a message on the Remind app. Go ahead and enter your answer now.